At first glance, Venus should not be the warning story. Place Earth and Venus side by side, and the comparison feels almost comfortable. Nearly the same size, nearly the same mass, similar density, similar internal structure. If you are looking for another world with the potential to resemble home, Venus would be near the top of the list. And that is exactly what makes it unsettling. Because the Venus we see today does not look like Earth's twin, it looks like something that went terribly wrong. Yet the deeper scientists looked, the harder it became to treat that outcome as inevitable. The measurements kept pointing back to the same uncomfortable fact. These planets were not born as obvious opposites. In many of the ways that matter most, they began remarkably alike. So imagine the scene billions of years ago. Two neighboring worlds, similar foundations, similar ingredients. One becomes the only known planet covered in oceans, life, and stable ecosystems. The other ends up almost unrecognizable. Somewhere along the way, the paths separated. And once that separation began, similarity stopped being a guarantee. That is the part that should hold our attention. Because if a planet that looked so much like Earth could become something entirely different, then habitability may be far less secure than it appears. Venus is not just a different world sitting next door. It may be evidence that worlds can start in surprisingly similar places and still end in completely different futures. Similarity was no longer the puzzle. Divergence was. The important question was not how alike these worlds began. It was what pushed them onto different paths. On Venus, the change may have started with something that sounds small. The planet warms. More water evaporates. More water enters the atmosphere. At first, that does not necessarily feel like a disaster. Water seems like part of a healthy world, part of a stable climate. But then the balance begins to shift. As more water rises into the atmosphere, more heat stays trapped. The surface warms further. That extra warmth pulls even more water upward. The cycle begins feeding itself. Now, the direction of movement matters. Evaporation increases. Heat trapping increases. Cooling starts losing ground. The assumption that the climate can simply correct itself becomes harder to trust, because each round of warming helps create the conditions for the next one. On Venus, the atmosphere is no longer just responding to heat, it is helping hold on to it. That is what makes water such a critical part of the story. Water is a greenhouse gas. It traps heat, and when more heat creates more water vapor, and more water vapor traps more heat, the cycle starts pushing in the same direction over and over again. This process has a name: runaway greenhouse warming. A feedback loop where warming creates conditions for more warming. And once that loop becomes strong enough, stability starts losing ground. You can picture the visible result: more evaporation, less water remaining where it was before, oceans beginning to decline while the atmosphere becomes increasingly involved in the process. And with each step, one of the planet's safety margins weakens. Venus has not become unrecognizable yet. The door to stability has not fully closed. But the climate is no longer standing still. It is beginning to lean. And once a world starts losing its ability to push back against change, the next question becomes impossible to ignore. Can Venus still steady itself? Or has one of its most important recovery systems already started slipping away? And at this point, the story seems almost finished. Look at a model of the solar system. Slide from Earth inward to Venus. The answer appears to be sitting right there. Venus is closer to the Sun. More sunlight reaches the planet. More energy arrives at the surface. More heat enters the system. Suddenly, the chain of events feels obvious. A warmer planet experiences more evaporation. More water enters the atmosphere. More heat gets trapped. The outcome starts to look less like a mystery and more like a forecast. In fact, the closer orbit gives Venus substantially more incoming solar energy. The measurements are straightforward. Venus sits nearer to the Sun, and that position exposes it to more radiation. For a moment, everything clicks into place. Venus was doomed by location. The planet started in the wrong place. If that explanation is true, the rest of the story should be simple. Move Venus farther from the Sun, and much of the chain reaction disappears. Distance becomes the answer. And if distance is the answer, there is an oddly comforting conclusion hiding inside the disaster. Earth is somewhere else. Earth occupies a different orbit. Earth receives less incoming solar energy. The comparison suddenly feels reassuring. Venus becomes the planet that never had a chance, while Earth becomes the planet that was simply lucky enough to be farther away. Venus was supposed to be Earth, but it was too close to the Sun. Simple, clean, predictable. The problem is that simple answers often feel strongest right before they are tested. And the closer scientists looked at Venus, the harder it became to know whether location alone could really carry the entire story. Then the simple explanation runs into a problem. The evidence does not point to a planet that was always dry. It points to a planet that lost something. On Venus, traces remained behind. Not oceans you can see today, but signs that water had once been part of the story. That changes the question immediately. If Venus once had significant water, then distance from the Sun cannot be the entire answer. A doomed planet does not lose what it never had. That is where the simple story starts to break. A planet doomed only by distance should not look like a world that lost something. But Venus does. And then, another clue appears high above the surface. Sunlight strikes water molecules and breaks them apart. The pieces separate. The light hydrogen rises higher and higher until some of it escapes into space. Not temporarily, permanently. Venus cannot simply pull that hydrogen back once it is gone. Scientists found evidence of this process in the atmosphere itself. Measurements revealed unusual enrichment of deuterium, a heavier form of hydrogen. Because deuterium is heavier, it escaped more slowly than ordinary hydrogen. The fact that Venus is jammed with deuterium is the definitive chemical footprint of a stolen ocean. Suddenly, the picture looks different. This is no longer a story about a planet receiving more sunlight than Earth. This is a story about a planet losing its fundamental internal machinery. When the water vanished, the disaster triggered a mechanical gridlock deep inside the crust. On Earth, liquid water acts as a critical lubricant for plate tectonics, allowing the crust to move and bury carbon deep underground. Without water, Venus's crust locked up. The planetary conveyor belt ground to a halt. Carbon dioxide had nowhere to go. It accumulated in the atmosphere until the air became 90 times thicker than Earth's, trapping enough heat to melt lead. The loss of water was not just a climate shift, it was a geological execution. Now look at Venus again. Not as the planet we imagined at the beginning. As the planet it became. A world that may once have had far more in common with Earth, now standing as a record of what happens when key stabilizing systems disappear. The lesson is not that Venus was unlucky. The lesson is that habitability was never guaranteed. Earth is not safe simply because it is Earth. Long-term habitability depends entirely on maintaining the stabilizing feedbacks that make recovery possible in the first place. Venus answers the title question in a way that is far more unsettling than the simple distance explanation ever could. What went wrong was not just that Venus changed. It was that Venus destroyed the very machinery required to change back.